But it is possible that some new form of particle, something else, could be discovered.
Yeah,
that we don't know about yet.
Because we almost know that there are other particles out there in the universe.
We almost know?
So a thing called dark matter.
Yes.
So we look out into the universe and we see that there's a lot of stuff there that's interacting gravitationally, but is not interacting strongly with the matter out of which we are made and the stars are made. So it's almost certain that that's some form of particle, that fits beautifully. And we see lots of different observations, the way galaxies rotate and interact, and even that oldest light in the universe, the so-called cosmic microwave background radiation, we see the signature of that stuff in that light as well. So we think that there's some other particle out there. And to be honest, we thought we would have detected it, I think, at LHC. We have lots of theories called supersymmetric theories that make predictions for all sorts of different particles that would interact weakly with normal matter. And I think it's broadly seen as a surprise that we haven't seen them at LHC. So that just may well mean that either they're a bit too massive, so we need more energy to make them, and we just haven't quite got enough, or we're not making enough of them often enough to see them, which is one of the reasons we're upgrading the LHC. So we also look for them, by the way, directly. So we have experiments under mountains. We bury them under mountains so the cosmic rays from space don't interfere with them. And we're looking for the rare occasions when these dark matter particles bump into the particles of matter in the detector. Because the idea would be this room's full of them. I mean, the galaxy is swimming with dark matter as far as we can tell, but it interacts very weakly with this matter, so it doesn't bump into us very often. So we're looking for the direct detection of it, and we're looking to make those particles at LHC.
So it's everywhere, but it doesn't interact with us?
Very weakly. So it interacts through gravity, and the archetypal particle that's everywhere that doesn't interact strongly is a neutrino. So we do know about neutrinos, we've detected those. And there are something like 60 billion per centimetre squared per second passing through your head now from the sun. So they get made in nuclear reactions in the sun. But they go straight through your head and then actually straight through the Earth, pretty much. Occasionally one of them bumps into something. And we can detect those because there are so many of them going through. But we only detect, I don't know, 1 or 2 a day.
And the idea is that dark matter encompasses an enormous percentage of the universe.
Yes, it's 5 times as much matter as dark matter than is normal matter. And the number is 25% of the universe. So roughly speaking, about 5% of the universe is normal matter, stars and gas.
25% is dark matter.
Yeah, so 5 is normal matter, about 25 is dark matter, and about 70 is dark energy.
That's the other thing I was
the other
going to ask
thing.
you about.
Yeah.
So what the hell's that?
Don't know. Know what it does. So again, if we go back, we talked about Einstein's theory earlier. So Einstein's theory, which works spectacularly well, says that if you put stuff into the universe, as we said before, then it warps and deforms and stretches. And it very precisely tells you, given the stuff that you put in it, how much does it stretch and how does it stretch. And the measurement we have is how it's stretching. So we observe, the thing we observe is how the universe is expanding and how that expansion rate is changing and how it's changed over time. So we have very precise measurements of that. So then we can use the theory to tell us what's in it, given that we know how it's responding to that stuff. And that's how we discovered dark energy. So we notice that the universe's expansion rate is increasing. So the universe is accelerating in its expansion, which is exactly the opposite of what we thought. And this is in the 1990s that we discovered that. So we can work out what sort of stuff and how much of that stuff you need to put in the universe to make that happen. And that's where we get these numbers from.
Was there resistance to that when that was first proposed?
Yeah, I remember one of my friends at Brian Schmidt got the Nobel Prize for that. And I remember I talked to him and he said, he was a postdoc, I think, at the time, so a young researcher. And he was making measurements of supernova, the light from supernova explosions, which are so bright that you can see them, hundreds of millions, billions of light years away. And he noticed that if you look at the data, the light is stretched in the wrong way. So we look at the stretch of light as it travels across the universe, and the universe is expanding. It stretches the light, so it changes the colour. And he noticed that there was a discrepancy, which said that the expansion rate is speeding up. It's been speeding up for, I think something like 7 billion years or so. It's been speeding up. So he thought that he's done something wrong because so he checked it and checked it and checked it, and he couldn't find anything wrong. So he did what a good scientist does, which is he published it so that somebody else could find out what he'd done wrong. And he said that he thought it would be the end of his career. He thought it'd be a laughing stock, and he got the Nobel Prize because he was right. It is stretching.
Wow.
It's a great lesson. It means that if you're sure that you can't see what you've done wrong, then you publish it. It goes back to that thing about humility we talked about earlier. We're not trying to be right. We're trying to find out stuff. And so a good scientist will be really happy if they turn out to be wrong because they've learned something. Now, and it's good that he took that path because he got the Nobel Prize.
Now, when he received the Nobel Prize and this concept started being discussed, what was the initial reaction to it?
Well, it's interesting because it's allowed in Einstein's theory, and it was in Einstein's original theory. So it's got a name. It's called the cosmological constant, and that's it's just allowed in the equations. And Einstein actually introduced it initially because Einstein's equations strongly suggest that the universe is expanding or contracting and not just sat there. So even before we'd observed anything, Einstein had a theory that suggested that the universe is just not static, and actually it really strongly suggests that there's a beginning, right? So the theory itself, on its own, suggests that you can see that if the universe is stretching today, then it must have been smaller in the past, right? Everything must have been closer together, let's say that. There's a man actually called Georges Lemaitre who worked independently of Einstein, but at the same time in the early 1920s, before we even knew there were other galaxies beyond the Milky Way. And they noticed that the equations suggest the universe might be stretching. And so he wrote to Einstein and said, your theory suggests there was a day without a yesterday. Because he thought if everything's expanding now, then it must have been closer together in the past. And so there might be a time when it was all together. And he was a priest.
Wow.
So he was a Belgian priest. So I wrote about this. Now, it's kind of my interpretation of it. But I think that he was more predisposed to accept what the equations were telling him, because a beginning, an origin for a priest is really a nice thing because it tells you the creation event.
Yeah.
And Einstein tried to dodge it and put this allowed term into his equation, which is almost the stretchy term, to say, well, if it's all kind of contracting or something, can I put something in to make it stretch a bit to balance it all out so it can be eternal? And you can't make it eternal that way. But he tried it. Then he took it out and called it his biggest blunder.
Taking it out was his biggest blunder.
No, he called putting it in his biggest blunder. Or at least some people think what he'd done was miss the prediction of the Big Bang, really. So by trying to fiddle around to have a static universe that's stable, he missed what the equations were screaming. His own theory was screaming to him, which is that, no, the universe expands or contracts. And he missed it, right? So I think that's probably what he meant by biggest blunder. But in any case, he took it out. And then later, in the 1990s, it turns out that, no, it's there. But it's really small. It's tiny, tiny effect. But it's still dominating the universe now. And it will dominate even more in the future. So we think that we're in a universe that will continue to expand, essentially doubling in size on a fixed timescale, which is about 20 billion years. So we think every 20 billion years into the future, forever, unless something happens, the universe will continue to expand and double in size.